Hey guys, welcome to Solving Related Rates. So at this point you should have already gone through the introduction, so you kind of know what related rates are and how to approach those problems. But as a review, we differentiate our variables with respect to time in real life. So before, when we were differentiating, we had different variables, usually x and y, but any kind of variable really. And we used power rule or quotient rule or change rule or whatever, and the variables stayed the same. Then when we differentiated using implicit differentiation, we had something that looked like this, that dy over dx, when we had y variables. So that is differentiating with respect to x when you had a y. Now we are differentiating with respect to time. So that's going to look like dy over dt, but also dx over dt, or any variable you could think of that looks like an m, but just whatever you want to put there, over dt. Differentiating anything with respect to time. So in differential calculus, related rates problems involve finding a rate at which a quantity changes by relating that quantity to the others that are known. The rate of change is usually with respect to time. So there is a strategy for solving for related rates problems, just the kind of steps that you would take in order to do it. So let's review those while we solve one. So a problem says you are blowing up a spherical balloon at a constant rate of 2 centimeters cubed per second. So 2 centimeters cubed per second. At what rate is the radius of the balloon changing when the radius of the balloon measures 10 centimeters? So we have that 10 centimeters. We know 10 centimeters is radius. So for radius, we can put r. That 2 centimeters cubed per second, it doesn't tell you exactly what it is, but you can approach it two ways. You can do it logically. You're blowing up a balloon, and so because of that, the air inside is increasing, so it has to be volume. Or just looking at this right here, that variable that you use, or that unit, sorry, that's centimeters cubed per second. So that has to be volume with centimeters cubed, but it's changing per second. So that has to be a rate. So it has to be a derivative over t, over d of t, and we can use v for volume. So the derivative of volume, or the rate of change of volume over time. Then the 10 centimeters is just the radius, and it says we need to solve for what rate is the radius of the balloon changing when the radius of the balloon measures 10 centimeters. So we need to find a rate of change of the radius. And so for that, we can have, again, another derivative. So d of something over derivative of time. But we can just use r, since we use r for the radius, for the rate of change of the radius. And so that is what we need to solve for. So when we think about it like that, I'm going to shrink this off to the corner there so then we can kind of have that there. So when we think about it like that, we want to set up an equation. So step one was, let's go back a little bit. Step one was assigning letters to all of the quantities that vary with time and any others that seem relevant to the problem. So we did that with the volume changing of 2 centimeters cubed per second, dv over dt. The 10 centimeters is r, and the rate of change of radius, we don't really know. Then we already did this. We identified the rates of change that are known, so the ones that I pointed to with the little arrows, and the ones that are yet to be found, because each rate has to be a derivative, so that radius is yet to be found. Now we need to find an equation. So we're looking at the change of the radius, and we have the volume, so we can just use the volume equation for a sphere. So volume of a sphere is 4/3 pi r squared. And we have these values. We have volume, or at least the rate of change of volume, but we can also solve for the original volume because we have the radius. We have radius and we have the rate of change of radius. So we have to take the derivative of this. Derivative of v is dv over dt. 4/3 pi is a constant. So we can just leave that as it is. Not a constant, sorry, a coefficient. We can just leave that as it is. And then we use power rule for r squared. So that is 2r. And then remember, since we're deriving in terms of x, we need to have dr over dt as well. So we know these values. We know dv over dt is 2. It's equal to, that stays the same, 4/3 pi times 2. We know r is 10. We don't know dr over dt. So we need to solve for dr over dt. So that means 2 over 4/3 pi times 2 times 10 is equal to dr over dt. I'll give you a second to plug that into your calculators and solve. Okay, so hopefully you've done that. When you solve this out, you either in your calculator get some kind of weird decimal thing, and that's fine, but check it with this answer. 1 over 200 pi, and that pi is going to be in the denominator. But wait, we need our units. So in order to find our units, what's changing? Radius. So if radius is changing, we need centimeters. And it's changing, it looks like per second, because that's when the volume was changing. So our final answer should be 1 over 200 pi. Now if you end up with a decimal, that's fine. You just need to make sure that that decimal is rounded to 3 points, or 3 decimal places. Your teacher might change that. Whatever they say, follow that. But the general rule of thumb is 3 decimal places. For problems like this, it's pretty easy to solve it out though. So I would recommend just keeping it at your fraction form. So we stopped at step 3, which was identifying the equation that we needed to have and what to do with it. So now then we had to differentiate both sides, which we did with the dv over dt equals 4/3 pi times 2r times dr over dt. And then you substitute all known rates, which is what we did by plugging in every single number that we had, and solve for the missing one. So it's pretty straightforward. It's just nice to have those steps memorized if you're that kind of person. Okay, let A be the area of a square, so we already have a variable. A equals what? Because we don't know it yet. The area of a square whose sides have length s. S we also don't know. And assume that s varies with time t. So that is telling us that we have a rate that is ds over dt. So the derivative of the sides, or the rate of change of the sides, with respect to time. And so that means the reason that they're telling you that is basically telling you that it's not constant. Those sides are changing. In some problems, they will tell you that it's constant. Or you'll get something with like a ladder or the side of a wall or something that can't be changed. And so that means the derivative is constant. At a certain instant, the sides are 3 feet long. Okay, so we have this, let's put a question mark here. This s that is equal to 3 feet and are increasing at a rate of 2 feet per minute. So 2 feet per minute. Remember, because this is a rate. How fast is the area of the square increasing at that moment? So we still need to solve for this. If we need to solve for that, we might as well have an area equation. So A equals, area of a square is length times width. That's probably the one that you're most familiar with. But if the sides are the same, then it's just going to be that number squared. So we can put S squared. Now we need to differentiate both sides. So, actually we can solve for the area here. Let's just cross that out. What we need to solve for is dA over dt. Don't really need to solve for the original area because when we differentiate that, that will no longer exist. So just a clarification, but not exactly necessary. So if we differentiate this, then we get the derivative of area with respect to time is equal to, use the power rule here, 2s times ds over dt. And then we plug in our numbers. dA over dt we don't know. That's what we're solving for. So 2 times s is 3, and ds over dt is 2. So 2 times 3 times 2 is 12. And our unit, because it's area increasing, that's going to be f squared, or ft squared, feet squared, per minute. And that's our final answer. It's important to note that it tells you increasing because sometimes it will be decreasing. And in those scenarios, you need to include the negative number or you will get the wrong answer. So if it tells you that it's increasing or logically you can confirm that it's increasing, always keep it positive. Otherwise, keep it negative. That's pretty much it.